Okay, so when you write um, this is an eigenvalue problem. This is an eigenvalue equation, and where again the psi sub n's and the lambda sub n's are the eigenfunctions and eigenvalues of the operator Q respectively. So in quantum physics, operators are always associated to physical quantities. I mean, operators that are associated to physical quantities always have real eigenvalues. That is, they have real, not complex eigenvalues. Because a physical quantity that you can measure has to be a real number. It can't be imaginary. That would not you would not be able to measure an imaginary quantity, and so if the operator corresponds to a physical variable, physical quantity, then the eigenvalues have to be real and not complex. And so, as we've discussed before, a couple lectures ago, a measurement of a physical quantity, for example, the energy eigenvalues of say a potential well, okay, even if the wave function is in a superposition state, measurement of a physical quantity can only result in one of the eigenvalues associated with that operator. Okay, you have to basically get a number back, and the number has to be one of the eigenvalues. And as soon as you make that measurement, you have determined that the system, the wave function, is in that eigenstate. Okay, and so the whatever eigenvalue you measure, whatever, for example, eigenenergy that you measure, tells you which eigenstate the system is in after the measurement. Okay, before the measurement, we would say that the system could be in a superposition of eigenvalues, of eigenfunctions, of eigenstates, but after you make the measurement, it basically has to be just after the measurement, it has to be in the state that corresponds in the eigenfunction that corresponds to the eigenvalue that you obtained. Okay? And this is sort of, in some sense, we call this the collapse of the wave function, or projection onto one of the eigenfunctions. It's an interesting and kind of deep concept in quantum mechanics. We're just sort of touching the surface of it here. Okay, so that's sort of an introduction. I mean, a little bit more about operators, and now we can talk about the commutation of operators. Okay, so when two operators, we can imagine that we can have two operators that we need to or want to apply successively, one after another, to the same wave function. And in that case, sometimes the order with which you apply the operators, that is, which one goes first, which one gets applied to the wave function first, might matter. Sometimes it might matter, sometimes it might not. Okay, so for example, if we have these two operators, the x operator, the position operator, which is just where you multiply by x, and the momentum operator, which is a derivative operator, minus IH bar d by dx. Okay, then if we apply the two operators in this order, xp, and this means that p operates on f first, and then x operates on what function results from the operation of pf. Okay, so you do pf first, and then you do x after that. Okay, so p is just d by dx times minus IH bar. So the minus IH bar, these are just constants, we can bring them out, and then we have d by df, and we multiply that by x. Okay, if we reverse the order, so we have px, then we first multiply by x, and then we take the derivative, and that is clearly not the same. In fact, if you basically subtract px from xp of f, then you get minus IH bar times x df dx minus f minus x df dx, and so these cancel, this one and this one cancels, and you're left with IH bar f. Okay, clearly not 0.